This is Albert, Daniel, and Brent, and our 203 final project is on safe multi-rate control with model predictive control and control barrier functions. Designing robots that can adapt to dynamic environments often requires continuous high-level planning, which is expensive and can be difficult to do at high frequencies. For a planar segue task, recent work has explored a multi-rate approach to this problem, which combines a low-frequency MPC controller for expressive high-level control with a high-frequency control barrier function-based strategy and maintains low-level safety guarantees. In our project, we explore a new application of this research. Rather than running it on the original planar segue task, we instead use it for controlling a 6-DoF quadrotor in a 3D world with obstacles.
For the high-level slow controller, we used reference tracking MPC. For the optimal control problem, we have a quadratic cost on the reference errors and control changes, and we have the usual constraints. Since the quadrotor has nonlinear continuous dynamics, we first linearize the dynamics and then tailor expand for the dynamics constraints. We also did not enforce the control constraint or terminal set constraint to encourage feasible solutions for the optimization problem. And this controller does not care about the obstacles and leaves it to the low-level controller. So we obtain our nominal control input I as defined here. The low-level, fast updating controller was based on control barrier functions, or CBFs. The basic idea of CBFs is that safety can be interpreted as the enforcement of the invariance of a safe set C as defined here. Similar to how reachable sets were defined in HJI reachability analysis, a CBF denoted by H parameterizes a safe set, and the CBF controller tries to enforce that H takes on only positive values during the trajectory. So we formulate the problem as a QP to minimize the deviation of I while satisfying the safety constraints, and the rest of the details are in the paper.
To test the multi-rate architecture, we designed a circular reference trajectory for tracking. In this experiment, we run the MPC controller at 8 Hz, and despite specifying pitch and roll constraints, the system destabilizes since the discretization is too coarse. On the right, you can see it basically ignores the constraint of 0.02 radians and blows up as a result. However, after adding a CBF controller running at 100 Hz, the system stabilizes and smoothly tracks the trajectory. On the right, we can see that the roll and pitch of the quadcopter hit the safety limits early on, preventing it from blowing up. Adding the CBF controller could be the difference between success and failure, especially for MPC controllers that may be slow or have feasibility issues. Finally, the multi-rate controller also does a good job reference tracking while avoiding obstacles. In this simulation, the quadcopter smoothly avoids these objects placed directly in the reference trajectory with minimal deviation. This makes it easy to use with any high-level controller as a safeguard and allows practical implementation with existing robotic stacks, which would be cumbersome to redesign. And that's it. Thanks to Professor Pavoni and the TAs for a great quarter.